Considering the inert pair effect on lead, the most probable structure of PbR2. So in order to solve this question, we must we must know about the what is the inert pair effect. So in the inert pair effect, the outermost two electrons will remain unhybridized. So in inner side electrons will remain unhybridized. So this lead means ns2 np2. Okay, this is the configuration. So these two electrons will remain unhybridized. Okay, we can say that these are inactive electrons. Okay, so here in the options they have given that lead dimer they have given, that means two lead atoms are there. So from this configuration we can make out that each lead atom must have one paired electron and one empty orbital. Okay, that means one empty orbital. So for this lead we have one orbital with two electrons and one vacant orbital. For this also one vacant orbital and one orbital with two electrons. So we can see this option in the in the given options. If you see that one, so here we have that option. Okay, here lead one orbital with two electrons and one is with empty orbital, another lead with empty orbital and two electrons. Okay, and why this option B is not correct? Because in the option B they have shown that this is, here they have not shown any lone pair on this lead atom, but here they have shown in the lead atom. But the lone pair should present on the both the lead atoms, and here also same and here also same. So the correct answer is this one. And the next question is, among the following compounds, the most shielded and deshielded pentadienyl proton respectively. So in order to solve this question, first we have to calculate the total electron count, or 18 electron rule. So if we will take option A, manganese means 4s2 3d5 7 plus this is 5 electron giving, and this is 6 electrons, total 12 18 this is 18 electrons are coming. 6 3 2s are 6, 6 plus 5. Okay, this is A, and B, this is comes under iron, like ns2 nd6, 8 plus 10, this is 18 electrons. And C also iron, ruthenium, osmium, they comes under same group, iron, ruthenium, osmium. And sorry, this is a this complex is present in +1 oxidation state. Okay, so if it is a +1 oxidation state, here the number of electrons will be, this will be 6. Okay, so total electrons will be 17 electrons. Okay, and remaining all three complexes are having 18 electrons complexes. So when they are given a series like iron, ruthenium, osmium, so as we go down the size will increases, right? And here we have a osmium to cyclopentadienyl and ruthenium to like this, and here the bond length is very small in case of iron. So we know that metals are electropositive. Okay, so metal gives electron density to the cyclopentadienyl ring here. Okay, so as we see in the case of osmium, because of bond length is more, it gives a less electron density to the cyclopentadienyl ring. But in case of iron, this gives more electron density, because the bond length is very small. Because of that reason, the more electron density will given by the iron to the cyclopentadienyl ring. So Among all the complexes, the one which is having more d shielded is this one. So D is the more D is the more shielded, because the bond length is very small between iron and cyclopentadienyl ring. So because of that, the electron density will transfer from the iron to cyclopentadienyl ring. Because of that reason, the D option is the more shielded. We see a more shielded cyclopentadienyl protons. And coming to the D shielded, so all the complexes are 18 electron complexes, but this complex is 17 electron complex. So here the electron density is less. Here in this case electron density is less. So because of that reason, so this is the D shielded, A is the D shielded, and D is the shielded. The answer will be D and A. This is an answer. The following statement are given regarding the acoustic interaction CH dash dotted line to iridium observed in IR PH3P thrice Cl. So they have given three options: upfield shift of CH proton in NMR spectrum, increased acid character of CH proton, and the IR frequency shifts to the higher wave number. So first of all, in order to solve this question, we'll draw the structure here. So iridium is here, P, this is 2 times. Here I have another phenyl ring, and here we have chlorine, PPH3 twice, and this is the structure. So now what is the acoustic interaction? Acoustic interaction is nothing but this hydrogen goes from here to here. Okay, so now this hydrogen is leaving from this carbon to onto the metal. So now it's very simple question. We'll take option A, upfield shift of CH proton in 1H NMR spectrum. This is correct. Why? Because when we have metal and hydrogen, okay, so the metal is electropositive, hydrogen is more electronegative than metal. So because of that reason, hydrogen takes electron density from the metal. So because of that, the hydrogen peak goes to the upfield shift. If you see the NMR spectrum of hydrogen which is attached to the metal, it comes in between minus 50 ppm to 0 ppm. Okay, so this is because of, so since metal is electropositive, hydrogen is more electronegative than metal, the electron density will be given by the metal and taken by the hydrogen. So the option A is correct. And then the second ones we'll see here, increase acid character of CH. Definitely it will increase, because so during acoustic interaction what will happens, the bond length which is present between CH, that will increases, and because the hydrogen is going towards metal, right? So because of hydrogen is going towards metal, this bond length will increases. So that means we can call it as acid character. Acid character of CH increases because the carbon is donating this hydrogen to the metal. So, and this is due to the bond length is increasing between the carbon and hydrogen. So this is also correct. And another one is IR spectrum, new CH in the IR spectrum shift to the high wave number. So this cannot be correct, because bond length is inversely proportional to the stretching frequency, right? So this answer is wrong, because here bond length is increasing. Because of bond length is increasing, it should go to the low wave number, not to the high wave number. So the correct statement will be A and B. So the C is the correct answer. A simple and important question. So here they asked about spin crossover behavior. So what is a spin crossover behavior? Spin crossover behavior means at high temperature, the spin will be high spin. A metal complexes shows at high temperature high spin, at low temperature it shows low spin. Okay, so here we have this complex iron phenanthrolene twice, NCS twice. So So they have given two temperatures, 250 kelvins and 150 kelvin. So 250 kelvin is high temperature. At this temperature it acts as a high spin, and at this temperature it acts as a low spin. Okay, and here so if you see the iron here, so here iron is present in Fe plus 2 oxidation state, that means 4s0 3d 6. So why this is plus 2? Here we have two negative ligands. NCS is a negative ligand, so because of that it is a plus 2 oxidation state. So at 250 Kelvin temperature, this act as a high spin. That means 1, 2, 3, 4, 5, 6. So the CFSC at high temperature will be, so this is 1.6 1.6 plus this will be 1.2, so this comes out to be 0.4 delta naught. Okay, at high temperature. And magnetic momentum will be how many lone pairs are there? 5 lone pairs are there. So 5 lone pairs means n into n plus 1, sorry, n into n plus 2. This principle we have to apply. 4 into 4 plus 2, so it comes close to 4.90 bm if you do this calculation. So at high temperature the CFS is 0.4 delta naught and the magnetic moment is 4.90 bm. And at low temperature, that is 150 Kelvin, so this will be a low spin. 1, 2, 3, 4, 5, 6. So here the CFSC is equals to 2.4 delta naught minus 2.4 delta naught, and the magnetic momentum will be here 0 into 0 plus 2. The overall will be 0. Okay, because here no unpaired electrons. The correct answer will be this is correct. This is the correct answer. So here we just need to remember that about the spin crossover behavior. At high temperature the complexes shows high spin, at low temperature complexes shows low spin. So as we know that how to calculate CFS and magnetic momentum, and this is also important question. Is here the reductive elimination of AR or coupled product from the A is phase element. Just remember, so in the reductive elimination, when it is more feasible means, so the R group should be electron releasing group. So when R group is electron releasing group, in that case the reductive elimination is more feasible. So among whatever the options they have given, so this option we can remove completely because here CF3 is there, and this option also we can remove because here CO is there, and this option also we can remove because here phenyl group is there, and this option we can choose because methyl group is electron releasing group, right? So this R group should be methyl group. Okay, then reductive elimination will be more feasible. The answer will be A. And the next question, this is the EPR spectrum. So I have made a G value, this is on the base of G value. So I have made 2 videos on the G value in my channel. You please watch that channel and in order to understand this question. So this is very easy question. This is also the reduced form of metal ion M in a complex is NMR active. On oxidation, the complex gives an EPR signal with G parallel is 2.2 and G perpendicular is 2.0. So this is the key point here. Okay, so G parallel, here G parallel is greater than G perpendicular. That means the electron density in dz square is greater than the electron density in dx square minus y square. So this is the condition we have. Okay, that means here 2 electrons are there and here only 1 electron is there. So from here we can make out that, so this is having 9 electrons only total, not 10 electrons. Okay, so mass bar spectroscopy cannot characterize the mass bar spectroscopy cannot characterize the metal complex and the metal atom is. So from this point we can remove tin, and we can remove iron also, because these two show small bar spectrum, and we have a zinc and copper here. So, and here what they have said that first you have to reduce it. Imagine that zinc we have, so we are reducing from zinc to zinc -1. So they are saying that this is NMR active. So upon oxidation we are, that means we will get back to zinc. Okay, so this is a D10 configuration. That means dx square minus y square dz square, both are having 2 electrons. Okay, so from this matter we can remove this also, and only option left is copper. So now we'll see the copper. Copper is 4s1 3d 10. So if we oxidize this, sorry, 4s0, if we oxidize this, this will become 4s0 3d 10. Okay, so this here we it's showing a Z out, because copper complexes shows gentle distortion, so Z out is more favorable compared to Z in. So from this condition we can make out that this is Z out condition, and the correct answer is copper here.